All right, my first calculus video failed, so I'm going to quickly go through the notes here and get you up to speed on integration by parts. So what I recommend you do is, consider pausing the video and maybe replaying some parts or something like that. I'll try and work kind of slowly, but things are already written, so it's, well, there it is. So anywho, you can also slow down the video's speed as well to kind of like, have more time to think about things or to hear what I'm saying and stuff like that. So anyway, integration by parts is the first kind of like new technique that we're learning in this new chapter that's about new techniques of integration, right? So last chapter on Friday we did all these old basic techniques that we had from the past that can still be put into kind of interesting or complicated ways, and they aren't easy necessarily, but they're still there. Whereas now we're going to be coming across some integrals that we could not do in the past, so we're going to add to kind of our toolbox or our toolkit when it comes to evaluating certain kinds of integrals and stuff. And like I said, the next strategy we're going to be here is integration by parts, or be using is integration by parts. Okay. It's useful for integrands that involve products of algebraic and transcendental functions. Algebraic functions, those like have like polynomials, stuff like that. Transcendental functions would involve things like sine, cosine, tangent. I think the trig stuff, but also like e to the x, natural log of x, those kind of things as well. Okay, inverse trig, stuff like that. So integration by parts is based on the formula for the derivative of a product, right? Or in other words, for the product rule, right? So when we take the derivative of a product like u and v, and in this case, we're treating u and v like functions, okay? Not like just like a variable u, a variable v. We're treating u and v like functions of x. And so then the integral of, the derivative of this product would be, the second v times the derivative of the first du plus the first u times the derivative of the second dv. Okay, so we have v times du plus u times dv. Okay, if we then integrate both sides of the equation there, okay, we're going to integrate then the d dx uv, right, from right there. We'll integrate the v du, we'll integrate the u dv as well, okay. Integrating this derivative, all right, results in the derivative in the integral canceling out and just duv, the uv there, okay. Integral of v du, though, harder to do because we're trying to integrate v with respect to u, which that's weird. Okay, we can't really do that. The variables don't really match up. Likewise here as well, the integral of u dv with respect to v, we can't do that either easily. So we kind of leave those integrals unintegrated. All right, but with some manipulation, if we subtract the v du over, we'll end up with u dv equals uv minus integral v du. Okay, this is kind of complicated to look at and hard to kind of like wrap your head around until we actually do a problem. But this is the format we're going to use here. So we're going to take an integral that's kind of in this form. We'll identify the u part of the integral, we'll identify the dv part, and then we'll set about rewriting it so that we do u times v minus the integral of v du. You'll notice here that when we're going to be choosing, we get to kind of break up the integral however we like into this part's going to be u and this part will be dv. That's our choice. But then beyond that, we want to be kind of like tactful about how we do that, right? So for example, u, you'll notice that in u, when we're going to rewrite it over here, we're going to reuse the u again, and then we're also going to have du. So typically you want to choose your u to be something that you can take the derivative of, easily. dv, you'll see, we're going to end up having to find v, right? In both cases we need v. So in other words, the dv, the thing we select to be dv, we need to integrate. All right, so that's something to just kind of keep in mind there. And so there again is our kind of formula for integration by parts. We're going to take an integral in this form and rewrite it in this form. And then hopefully that will allow us to integrate this a little bit more easily. All right, some guidelines. Try letting dv be the most complicated portion of the integrand that fits a basic integration rule. Okay, so you want to kind of like let dv be as much as you possibly can of the integrand, and but also make sure, of course, it's going to fit a basic integration rule because we're going to have to integrate dv to get the v's here on this other side. Okay, try letting your u be the portion of the integrand whose derivative is a function simpler than u. Okay, so something that when you take the derivative, so let u be something that when you take its derivative, it becomes simpler than u was in the first place. Okay, So for example, x squared becomes just x, or natural log of x, its derivative becomes 1 over x. So those are good kind of choices sometimes for your u. And then number 3, dv always includes the dx of the original integrand. Right? When you integrate something, it'll be with respect to x, with respect to t, sometimes, whatever. Your dv should always include the dx or the dt, whatever those, whatever you're originally integrating with respect to, that should be in your dv. All right, so a final little help here, also a little strategy for you to use when it's time to pick what your u is going to be. All right, is this like mnemonic device, ILATE, okay? However you want to read that, I-L-A-T-E. I stands for inverse trig, so you want to pick your u to be an inverse trig function first, if that's what you've got, and then second natural log, and then algebraic functions, then trigonometric, and then finally exponential as your kind of like last resort there for your u. All right, and then of course we don't really have a guideline for picking your dv, because once you have your u selected, the rest of the integrand has to be dv, okay? So that's all there is to it. All right, so let's take a look here at, we want to integrate the following using integration by parts when necessary. So our very first problem here, so again, I rewrote the integration by parts rule up here. Our very first problem, right, is written right here. If you kind of just consider this without looking at my work, you'll see that this is something that we couldn't integrate before, right? We could not integrate this prior to, to today, right? We don't know how to integrate something like this. 3x squared times the natural log of x. We could try U substitution, but what would our u be, right? It just wouldn't work out. So we're going to try integration by parts. And of course, the directions say integration by parts, which, in the future, right, when you're doing these kinds of problems, you won't have the directions telling you use integration by parts. So you'll need to know, or you'll need to be able to discern and navigate when you're supposed to use integration by parts and when not. All right, and basically, for all intents and purposes, integration by parts is kind of like a last resort, just because it is, a little more complicated, a little more work. So you want to try and integrate with another strategy first, and then you go to integration by parts. Anyway. So in this case, right, we can see we have some functions to pick from to be our u. If we go back to our hierarchy here, we have inverse trig, right, is first, but we have no inverse trig in this problem. The very next one, though, is natural log, and we do have natural log. So we're going to let u be the natural log of x. And if we let u be the natural log of x, then that leaves the 3x squared dx must be our dv, and you'll see I did that right here. Now, understand, I put the integral symbol in later, okay? So I just had dv equals 3x squared dx first, because we need to come up with v, so I integrate both sides. So v is x cubed. And then if u is natural log of x, then du is 1 over x dx. Okay? Armed with these pieces of information, we can then substitute in for uv and the v du. Right? v is going to be x cubed. All right, we said v was x cubed, so there it is. U is ln x, natural log x, minus, and then there's our integral x cubed times 1 over x dx. So that x cubed and 1 over x can simplify to just x squared, right? We multiply them, and now we have something we can integrate, okay? And so we do finally then integrate that minus x squared, or minus integral of x squared. We integrate that to be minus 1/3 x cubed, and of course the plus c. And at this point we're done, right? Because there's nothing left to integrate. So that is our final solution. X cubed, natural log x, minus 1/3 x cubed plus c. Okay? This part continues right through, but we have to integrate that still there. So we got the final answer. And of course, don't forget the plus c, it is an indefinite integral. All right, moving on to letter B. I'm trying to squeeze this all on there. There we go. That fits. All right, so letter B, again, we have like x and then e to the 2x over 3. Okay, following our hierarchy here, if we go back to the other page, we have x and an e to the something. Well, we don't have inverse trig, we don't have natural log, we do have algebraic. You see, the very end is exponential. Algebraic, we want to do that first before exponential. So we're going to let u be the x. So if u is x, that means du will be 1 dx, right? The derivative of x is just 1. And if we let our dv be x e to the 2x over 3 dx, e to the 2x over 3 dx, okay, we integrate both sides here. Well, to integrate e to the 2x over 3 dx, we have to use a U substitution. I chose to use a W substitution here, though, and the reason for that is because we already kind of used U as a variable, and so we should really use a different variable there for good mathematical kind of like, practice. And so we'll let W be 2x over 3, and I kind of like, there's the integral e to the 2x over 3, and I kind of just jumped to the answer there. I did the actual work for the integral of e to the 2x over 3 right down here, just kind of like make it easier. And then I took my answer and put it right up there for where v was. Okay. Once we had those pieces, again, we did u times v, so 3 halves x e to the 2x over 3, right there, here's uv, minus the integral of v du. So v, 3 halves e to the 2x over 3, I put the 3 halves out front, e to the 2x over 3, and then du is just dx, so there's that. And then to integrate e to the 2x over 3, it's pretty straightforward, right? It's going to be another application of this w substitution, and so I just went ahead and rewrote that, e to the 2x over 3 as e to the w, with the 3 halves in front, because again, we had another 3 halves for that substitution. And then integral e to the w gives us e to the w minus the 9/4 there, plus the c, because now we finish integrating. All right, and then I put the substitute back in for the w, which was 2x over 3 right there. And so there's our final answer. All right. And again, I'm sorry I can't ask you any questions. If this goes too fast or something like that, or you want to, please check with me, Mr. Widmeyer, or check with Mr. Goff, right? We'll both be happy to answer any questions you might have on the notes here. I apologize for the drawings of my V's and my U's. I'll try and make them, my V's more pointy and stuff like that, and my U's less pointy. All right. Last one here, x squared equals x squared times cosine x. All right, I let u be x squared, all right, and v then had to be, dv was cosine x dx. Again, we choose the algebraic function first because it's ILA, right? I for inverse trig, we don't have any inverse trig to pick here. L for natural log, we don't have a natural log. A then for algebraic. So we're going to let u be x squared. du is 2x dx. Okay, and then that means dv has got to be cosine x dx. Integral of cosine is sine of x. So v is sine of x. Okay, when we go and rewrite it here, so there's uv minus the integral of v du. Okay, and then I rewrote it somewhat there. You'll see we have x sine x. Well, we can't integrate that using normal rules. We're going to have to use integration by parts again, which is why then I added these little sub 1s in here, these little subscript 1s, to show that this was u1 du, du1 dv1 v1, and then I did u2 du sub 2, dv sub 2, v sub 2, because we had to do it all over again, now letting u sub 2 be x, du sub 2 being 1, and then, because again, the derivative there, and then sine of x dx, integrate that, we get dv sub 2 equals negative cosine x, okay? And then we rewrite this, so we're bringing everything down, right? There's x squared sine x still, there's the minus 2, and then parentheses, because we're going to rewrite this integrand as parentheses, uv minus, but it becomes plus positive, integral v du. And then finally you can integrate that cosine x, right, to be just sine of x plus c. And then you can finally distribute the negative 2 there and get our final answer. You can stop right here at this step, this second to last step right here, the penultimate step, that's fine. Your choice, matter of preference there, all right, matter of preference. All right, number 2, moving on there. Okay, we're trying to find the area of a region bounded by the x-axis, the graph y equals arc sine of x, and 0 and 1, x equals 0, x equals 1. All right, this is an integration, right? This is like an application of integration. We've seen this in the past, right, where we just did an area of a region between two curves. I guess our two curves here are the x-axis and the y equals arc sine x. Anyway, we're going to integrate from 0 to 1, arc sine x dx. Integral of arc sine, we don't know how to integrate arc sine. We can take its derivative, but we don't know how to integrate it. So guess what? We're going to try integration by parts here. We're going to let u be arc sine because arc sine is an inverse trig. That is like the highest, priority to be u in our little mnemonic device there, I-L-A-T-E, ilate. Why? Because derivative of u is going to be 1 over the square root of 1 minus x squared dx. Okay? And then that leaves then, well, if arc sine of x is our u, that leaves just dx to be our dv, and therefore v will just be x. All right? So with that, then rewriting things, so uv, x arc sine x, minus the integral of vx times du, it's going to be x over the square root of 1 minus x squared. This we can integrate using a substitution, using, again, a u substitution, or I'm going to use a w because we already used u's and stuff. So let w equal 1 minus x squared, dw equals negative 2x dx, negative 1/2 dw equals x dx. And so this we'll rewrite to 1 over w to the 1/2 with a 1/2, or minus or negative 1/2 in front, but it's minus negative 1/2, so I made it plus positive 1/2 there, dw. Okay, 1 over w to the 1/2 is the same thing as w to the negative 1/2. So when I integrate that, we're going to add 1 to negative 1/2, make it w to the 1/2, divided by the new power, divided by 1/2. Same thing as multiplying by 2. 2 times 1/2 cancels out, it's just 1. So we have x arc sine x plus w to the 1/2 plus c. We're going to re-substitute back in for the w there, 1 minus x squared. And then finally evaluate. Don't forget, right, the whole purpose of this was to evaluate the definite integral from 0 to 1. So now we're going to plug in 0 and 1 for our upper lower limit. Okay, plug in the 1, x 1 times arc sine of 1 plus 1 minus 1 squared to the 1/2 minus plug in the 0. And be careful, right? If your lower limit of integration is 0, the temptation is to just say, oh, my lower limit goes away, right? If it's 0, it should just all be 0. No, not always the case. Please make sure you plug in that lower limit of integration if it's 0, okay? Because you want to check to make sure that it does, in fact, equal 0 before you assume so, right? Don't assume it, because we don't know always that it will be that way. And it won't always be 0 if it's 0. For example, here, right? 0 times arc sine of 0, that is 0. But when you plug in 0 into the 1 minus x squared, it's 1 minus 0, which is 1 to the 1/2 is 1. So you're going to subtract a 1 there. This simplifies to pi over 2. So we have pi over 2 minus 1 is our final answer there. Okay. Example 3. All right. Let f be a differentiable function such that u times dv equals, such that f of x times the sine of x dx equals negative f of x cosine x plus the integral of 4x cubed cosine x dx. Okay. Now again, this is nice because we're doing this, right in the middle of our integration by parts. So it's like, clearly, Mr. Witt, this is going to be an integration by parts question. Now, when you're on the AP test, right, you're going to have to look at this and identify, oh, this is integration by parts. This is from an old AP test. You can tell it's an older one because it's got 5 options instead of 4. Your test will have 4 options on it. Okay, but you can kind of see the integration by parts nature of it, right? We have, 2 kind of parts to our function there. We have, u times v plus integral v du and stuff like that. And so I try to break this down here to kind of show you what was going on. Okay, if you look here, to identify, which part's u and which part's dv, I kind of go to the second piece right here, right? And you'll see that the f of x repeats, whereas the cosine is not a repeat of sine. So from here to here, right, the thing that repeats is the u, right? U repeats. We have u dv here, and then we have a uv here. So that means u has to be f of x. Now, you might be tempted to say, Ms. Whitmire, isn't u negative f of x here? Well, no. The negative comes from the cosine, right? If dv is sine, right, and sine would have to be dv because if u is f of x, then the rest is dv. dv is sine, then the integral of dv, right, the integral of sine is negative cosine, and there's where the negative comes from. It's from the cosine, actually. Okay? Which means then we're going to have minus the integral of v du, but it's really plus here. Why is it plus? Because v was negative cosine, and minus the negative becomes plus positive. And that leaves then that the du, right, it's v, there's the v that we saw earlier, right, v, du, that means that's the 4x cubed. So if du is 4x cubed, integrate backwards, x to the 4th. Okay, which is letter E there. All right. Very last one here, we didn't get to finish up. We'll finish this up tomorrow, so you get to see it in the video tomorrow, hopefully, at normal speed and with student interaction and stuff like that. Again, my apologies. The video crapped out on me or something like that, so hopefully it's going to be fine for this second go around. Example 4 here, solve the following differential equation for y equal to f of x, given dy over dx equals y ln x, and f of 1 equals 1. So there's our differential equation, dy over dx equals y natural log of x. What's our technique we use to solve a differential equation? Well, the one technique we have is separation of variables. So we move the y over, make it 1 over y dy, move the dx over, so it's ln x dx. And they're going to integrate both sides here, right? Because we want to get y equal to f of x. Integral of 1 over y, easy, natural log of the absolute value of y plus c, equal to the integral of natural log of x. Now, the natural log of x, right, we can take its derivative, but we don't know how to take its integral yet. We're going to do it now, and we're going to do it with integration by parts. So we're going to let u be natural log of x because, again, in our hierarchy, okay, I, inverse trig, we don't have that. L, natural log, aha. So u is natural log. That means du is 1 over x. dx there I should have. And then our dv then is going to be just dx. That's all that's left. And so they integrate dv and dx, we get v equals x. And then that's where I stopped, okay? But you can, you could proceed from here if you wanted to. We have uv minus the integral of v du. And you can kind of see how it's going to work out there. It's not too crazy. But again, we'll stop there and finish that up on Monday. Sorry, Monday. Today's Monday. On Tuesday, tomorrow. Okay? So again, if you have any further questions, feel free to go back through this video or talk to me or Mr. Goff, and we'll be happy to help you out.